Okay, welcome back everyone. In this video we're going to be looking at an extremely important concept, the electric field. And so what I'd like to do is to go back for a moment to when we were talking about gravity and remind you about what the gravitational field was. Now we talked about this in a couple of different ways. First of all, we said, okay, if I'm standing at the surface of the Earth and I'm just looking at a small part, it's relatively flat, which way is the force of gravity? Well, you'd probably agree that the force of gravity just points down, and everywhere in space it has a value of mg. This is at the Earth's surface. And we also said that we can calculate the acceleration of something with a mass of m if we take the force of gravity and divide by its mass, right? F equals ma. So mg over m. And this tells us that our acceleration is g. Okay. And then we also talked about drawing the large Earth with continents and everything and ice caps, and you get the idea. Okay, and there's the bell again. And we talked about if we had a tiny little astronaut in various places, what would be the direction of the force of gravity acting on him or her? And we said that pretty much it would be down like this. And we calculated a value on further away it would be less, and closer it would be more, things of that sort. And we calculated a value for this so-called gravitational field. And we said that the gravitational field is the ratio of the gravitational force divided by a small test mass. Okay, so big M for the Earth, little m for this little astronaut. And we calculated the gravitational field. And we saw that this was g big M little m over r squared, which is the force of gravity, divided by little m, which cancels, and we said that the gravitational field was gm over the radius of the Earth squared. I'm turning r into the radius of the Earth. And we gave that a special name. We did the math, and we found out that this was 9.8, and so that is what we call g. So, just to recap, g, little g that is the value of the gravitational field at Earth's surface. Well, that's our 9.8 anyways. And then if we go anywhere else, it's technically radius of the Earth plus our height squared. And that's just acceleration. Okay, now, the other thing is that this gravitational field is a map of gravitational forces. Okay, so now what we're going to do is bring this to the electric force. And the reason behind this is pretty clear, okay? With gravity, we have a force of gravity which is g m1 m2 over r squared. With electric charge, we have a force which is a constant times the two charges divided by r squared. So we have a natural parallel, and we said that the gravitational field G was the force of gravity divided by one of the masses. So if I were to call this big M and little m, then this would be big G big M over r squared. Okay, likewise, there is an electric field, and the electric field has the value of the electric force divided by what we call a test charge. And this test charge is always positive. Now with gravity it doesn't really matter. Masses aren't positive or negative, they're just masses. But with the electric force we have to pick, because the electric force can either be attractive or repulsion. And so we're just picking that this is always going to be positive. And so if I rewrite this as k times big Q times little q over r squared, then I can write the field as k big Q little q over r squared divided by little q. Or in other words, the field is kq over r squared. The little q's cancel. Okay, now what does this look like? Well, let's draw not the Earth, but let's draw a charge. And let's say that this is a negative charge to make the analogy clearer. Okay, now what I'm going to do, and this is charge big Q, this is the charge which is creating a field. Okay, now I have to be careful because this little q is our so-called test charge, and it's designed so that little q itself does not have a significant electric field. Okay, so it's very small, it's very tiny. It's like saying, okay, what's the gravitational field of an apple compared to the gravitational field of the Earth? If I were to drop an apple, the Earth wouldn't go up to meet it very quickly. And so this is a similar thing. We want to take a look at the force acting on this test charge, and we don't want this test charge to affect the charge which is making the field. Okay, so which way would be the electric force on a tiny positive charge? Well, it would be that ways. And if I brought it over to here, it would be that ways. And over here, be that ways. And you get the idea. So what I'm doing is basically I'm drawing a map of electric force. And that is another way of thinking about the electric field. Okay? Now there's two other things that I want to say. One is that G for gravity is the force of gravity divided by a little mass, and the units are newtons per kilogram. So instead of saying 9.8 meters per second squared, we could say that the Earth's gravitational field causes 9.8 newtons of force for every kilogram of mass. That's worth writing out. Okay? The Earth's gravitational field at the surface causes 9.8 newtons of force on every 1 kilogram of mass. This is a very important way of thinking about the gravitational field, because this allows you to think about the electric field in a way that makes more sense. And so what we can say about the electric field, E, which is the electric force divided by a test charge, this is newtons per coulomb. In other words, the electric field causes, let's just say I pick a number, that my electric field is 1,000 newtons per coulomb. It causes 1,000 newtons of electric force to every 1 coulomb of charge. That's a very important way of thinking about what the field is really doing. Okay, and now finally, the last thing that I want to say is that in order to have a force, you need to have two objects. You need to have two masses, or you need to have two charges. Well, with the field, this is not the case. With the field, you only need to have one object, which is creating a field. In other words, a field is a set or a map of possible forces. Okay? If I have a charge, and let's say I do a positive charge, it has an electric field that points outwards. And what it says is that if I place down a positive point charge anywhere, it's going to experience a force outwards. Okay? Now if I don't put a charge down, I still have a field. Okay? But in order to get a force, I need a second object. So that's a very important distinction between force and field. With a force, you need two objects, but with the field, you only need one. Okay? And in later videos, we'll talk about how you can have different types of electric fields. But first, a very quick preview. Okay? This is the electric field caused by what we call a point charge. And we'll talk about different types of fields, and you'll explore this in a couple of different computer activities. But sometimes you'll come across a place where there's just a field already sitting in space. Okay? So this is what we call a uniform electric field. It's just there. How to get there? We don't know. Now it could be that outside of our field of view, there might be something right here, and there might be something right here, two objects that have charge that are causing a field to form, but we don't know about that. And by the way, this is one way that we can cause a field to go left to right, is to put positive charges on the left and negative charges on the right. Because then, if I put down a positive test charge, what will the guys on the left do? Well, they'll push it away, and the guys on the right, they'll pull it towards. Okay? But this is a uniform electric field, E, as opposed to the field produced by a point charge. Okay, more on this later.